Hello and welcome to Extreme Solution Essentials, the IP Campus. So today we're going to be looking at the following topics. The products that we use to build the IP Campus, the VSP switches, the Exos switches and the ERS switches, and also the technologies that we use inside the IP Campus, stacking, clustering, our recently launched Extended Edge and the EAPS service. And then finally, we'll look at a few campus network designs. So you may know that the extreme flagship campus solution is the automated campus. However, there are cases where this is not appropriate for the customer. Maybe they're an existing customer that is already using the legacy technology and they want to continue on that path. Many of the concepts that we use in the IP campus are also completely relevant to the automated campus, such as stacking and clustering. So it's worth being aware of them. Okay, so here we can see the switches that we use to build the IP campus solution. On the left you can see I've tried to indicate the port speed, so basically the higher the switch, the higher the switching capacity and the higher the port speeds that it can support. On the left we have the VSP, or Virtual Services Platform switches, which are fixed configuration, cluster capable switches. And right at the top of there you can see the VSP 8600, which is the high-end chassis clusterable switch. Next we have the Exos series of switches, a very varied range of switches ranging right from medium range campus access up to 100 gig data center top of rack or core capable switches. Next we have the ERS switches, which is a relatively simple range of switches delivering cost-effective stacking with high throughput and bandwidth for the campus edge. Then we have the EOS switches, which are really an SMB range of switches, occasionally used in campus networks, so put on here for inclusivity. And then finally the VPEX switches. These are virtual port extenders that are used in our Extended Edge solution, as we'll talk about shortly. Now let's look at some of the characteristics of the switches here and what holds them together. If you look at this range of switches that I've highlighted, these are actually the switches that are capable of delivering PoE to the access port. These are the switches that you would normally position in the access layer of the network rather than the core or distribution. However, they do have features that can be used in the distribution or core layers, so sometimes, depending on the customer, we may position them. But generally, it would be this group of switches here that we would be building the IP campus core and distribution network with. If we look at the next group of switches, which I've highlighted here, these are the switches that are capable of being stacked together. We take a number of switches, up to 8 normally, we connect them, sometimes using traditional Ethernet ports, sometimes using dedicated stacking cables, and we build them into a virtual chassis that's managed from a single IP address. The next group of switches highlighted are the switches that are capable of clustering. Clustering is a technology where you take 2 switches, you associate them together, they're connected using traditional Ethernet ports, and they become a logical virtual chassis from a layer 2 perspective. And then the final group of switches that I've highlighted here are the ones that are capable of acting in our Extended Edge solution. The Extended Edge solution has 2 components, the controlling bridge switches, the brains of the solution, highlighted here, and then the actual port extenders, which is the V400 series highlighted here. And then finally the EAPS capable switches. EAPS is a ring technology used to build resilient layer 2 rings, which we'll talk about in a moment. So now let's have a look at stacking. You can see a couple of examples of stackable switches just here. The benefits of stacking are basically that we take the group of switches, we connect them together using some sort of technology, sometimes Ethernet, sometimes dedicated stacking points, and we form them into a single virtual chassis. We manage that chassis from a single IP address, so it simplifies the management of the network. The switches are actually logically connected in a ring, and traffic will actually flow both ways down the ring, depending on which is the shortest path, to maximize the bandwidth that's available on the stacking backplane. One of the useful features of stacking is that we can terminate lags or link aggregation groups across different units in the stack which gives us active-active load balancing links and a high level of redundancy in the event that one of the switches should fail. Stacking is generally used at the access layer of the network, in the IDFs where we're going to connect the user devices. However, the technology can also be used in the core and in the distribution of the network when appropriate, and it's really down to the customer requirements. When we form switch stacks, there's a general rule that we're only allowed to put 8 units in a single stack. So if we require more than 8 units, we actually have to create 2 stacks. One thing to note is the X220 series switches, which only support 4 units in a stack. All the other range of switches can support 8 units in a single stack. One point to note about stacking is that all switches in the stack must run the same software release. If we try to stack switches that have different software releases on, the stacking will fail. So it's important to put the same software on before we actually attempt to stack them. Now we'll look at a particular type of stacking that's used by the Exos switches. It's called Stack 5. Stack 5 uses native 10 gig ports, so we don't have special stacking ports. It has 40 gig of bandwidth from each switch. And just let me explain that. If we take one switch, 2 of its 10 gig ports will be used for stacking. Each 10 gig port is capable of 10 gigabit in and 10 gigabit out. So that's 20 gigabit if we add the bandwidth of both the ingress and the egress for that port. And then of course we have 2 ports. So if we add the 20 to the 20, we say that the stacking bandwidth of each individual switch is 40 gig. Stack 5 is supported on all the Exos switch range except the switches that I note here. These are high bandwidth, high performance switches, so they actually use a different type of stacking to make the most of the switching capacity of the switches. But all of the other Exos switches are compatible with this technology. It allows different models of switch to be stacked together. So for example, I can take an X440 and I can stack it with an X460, even though it's a completely different model from a different range. This form of stacking also allows long distance stacking. Since we're using the traditional Ethernet ports, the 10 gig ports on these switches to do the stacking, if it's an SFP plus port, we can put a laser transceiver in that could have a distance capability of 40 kilometers. So we could make a stack that's actually spreading across a huge geographical area. Sometimes this is appropriate, but normally stacking is used in a small area in an IDF, for example. One thing to be careful of with the Exos stacking is remembering that the switches have to have the same software release. If you're looking to stack different generations of Exos switch, for example, the 440G1 and the 440G2, it's important to check that those switches can actually run a common software release, because in some cases it's not possible. So do be aware of this when adding switches to an existing network. So now we'll take a quick look at the other types of stacking used on the Exos platforms. We can see here the V400, the V320, the V160 are high performance stacking. These are giving 400 gig, 320 gig, 160 gig of bandwidth for each switch in the stack. But as you can see from the models indicated, it's only supported on Pacific models that have a very high performance switching capacity. The one at the bottom there is actually used by the 450, which again is a slightly unusual one because the 450 has dedicated stacking ports. The ports on the back of the 450 are not traditional Ethernet ports, and they can only be used for stacking. The other types of stacking, the V400, the 320, are actually using traditional Ethernet ports on the switches, but if you look at the type of Ethernet port, it's the high performance QSFP Plus or QSFP Plus 28 types. The ERS switches use dedicated stacking ports on the back of the switches. If you look at the models listed here, they cannot be stacked together. So for example, an ERS 5.X can only be stacked with other 5-something models. Same goes for the 4, same goes for the 3. The difference on these switches is basically the stacking bandwidth, and they use dedicated copper cables that are available in the distances 1.5 meter, 3 meter and 5 meter. The stacking cable on the 4900 is actually included with the switch, so that's worth knowing when doing bill of material. And then finally the X220 stacking, Again, it's a relatively low bandwidth stacking protocol. It uses 2 of the SFP plus ports on the switch, and do note that unlike the other switching technologies, the X220 can only support 4 switches in a stack. So now let's take a look at the next technology that we use in the IP campus, and that's switch clustering. Switch clustering is very commonly used between pairs of core switches and distribution switches. It basically works by taking 2 switches, we connect them together in a redundant way, and we inform each switch about his peer. At that point, the switches exchange forwarding database and they become aware of each other's port link statuses. So from a layer 2 perspective, it's as if they become a single switch. When we connect a third-party device using a lag, such as maybe another switch or a firewall or maybe a server running teaming, we can actually run that lag to the 2 different switches, so it's terminating across different chassis. This provides active-active load balancing and redundancy. Note that with switch clustering, the switches are still managed as 2 individual entities. So from a management perspective, I still have 2 switches. It's just from a layer 2 perspective, they become 1 virtual switch. With switch clustering, you can only have 2 switches in a cluster. Unlike stacking that supports 8, it has to be configured in pairs of switches. Also note that the switch clustering is not compatible between the XOS and the VOS switches. So when we're clustering switches together, we must cluster 2 VOS switches or 2 XOS switches, not a VOS switch and an XOS switch. It simply won't work. Also note that XOS stacking is compatible with switch clustering. So we can take an XOS switch, we can stack it with a number of other XOS switches to form a larger virtual chassis, and then we can cluster it with another XOS virtual chassis. So this allows us to use the benefits of both technologies together. Switch clustering is normally used in the core and distribution layer. It provides very high resilience and active-active load balancing. However, sometimes it's used in the top-of-rack layer for servers, and there's a particular reason for that. If you think in a data center top-of-rack, we have 2 switches. If we stack these switches together, we would take the server and we would connect the server 1 port to one switch, 1 port to the other switch. This would provide resiliency and load balancing. However, when it comes to upgrading the software on a stack, we can't upgrade individual units. Remember the rules. All software on the units in a stack must be running the same release. So we're not actually able to perform a software upgrade on the stack without having an outage for that server. Even be it a few minutes while the switch reboots, we are going to have some downtime. If we use switch clustering, we're not limited to having the same software release on both switches. So what we can do is upgrade the first switch in the cluster, wait for it to recover, wait for the cluster to reform, and then upgrade the second switch. So for this reason, switch clustering is often interesting when proposing switches for top-of-rack layer as well. Now if we look on the slide here, we can see the common topologies that are used in switch clustering. The first is the triangle topology. We have a pair of switches clustered together, and then we have access switches which are dual homed back to the cluster pairs. This is often used in the access layer of the network for the IDFs to attach to the distribution switches. The next example is a square. Here we have a switch cluster actually attached to another switch cluster. This would be used potentially between the core and distribution layers of a network. At both the core and distribution we need full resilience, we need high availability, so we place 2 switches there, we cluster them together, and we actually create a lag between the 2 clusters. And then the final example here is mesh, which is basically the same as a square, but with some extra links to make the design more redundant, if we have the fibers available to do this. So now let's compare stacking and clustering. The reason I want to do this is they are similar technologies. With clustering we can only use 2 switches, with stacking we can use 8, but they provide a very similar function from a layer 2 perspective in the network. However, there are benefits and disadvantages with each technology, so we must ensure that we use the correct one for the customer requirements. The first is management. From a management perspective, a stack wins out. It has a single IP address to manage it from, a single CLI or a single GUI interface. We don't have to manage two nodes. So from a customer perspective, it's easier to manage. It's a single node, even though it has resilience. From a distance perspective, as in how far we can place the units apart, clustering wins out. With stacking, we're sometimes limited to particular types of stacking cable, which can limit the distance that we can split a stack over. Think of a customer that has 2 data centers and they want to split between the 2 data centers. With stacking, it may not be possible. With clustering, we always use the traditional Ethernet ports, be it 1 gig, 10 gig, 40 gig, or even 100 gig. And we can actually make use of the different types of SFP or QSFP that are available for those switches to make the distance between the clustered pairs as far as we want. So clustering wins out. When we look at software upgrade, it's difficult to pick a win here. When we're upgrading a stack of switches, it is simpler to upgrade the software. We simply upgrade one unit on the stack and it handles the upgrade of all the other units. It's done completely automatically. However, if we think about the top of rack example that I gave earlier, this is not always desirable. When we're upgrading the software on clustered switches, we do have to do 2 switch upgrades. We have to upgrade the first switch, followed by the second switch. However, we have the flexibility to upgrade them at different times and prevent taking the network down completely. The next one is configuration. So again, a stacked switch is easier to configure simply because it's a single point of configuration. With a cluster, we have 2 distinct configurations, and when we're making changes to the network, we have to go and configure each of the members of the cluster. And obviously it's up to us to ensure that we actually configure them correctly and the same. If we look at failover, the 2 technologies are very similar. Stacking will fail over very quick. If there's a switch failure or we break one of the links in the stack, we will have sub-second recovery. However, with stacking, one of the switches in the stack will actually be the master node. It's basically controlling the higher level functions of the entire stack. One example is OSPF. If we're running a routing protocol on a stacked switch, if the master switch fails, the next switch in the stack will absolutely take over, but it will cause the routing protocol to restart. So from a layer 3 perspective, we might have a small amount of traffic loss. When we're running switch clustering, the routing process, if we're using layer 3 protocols, is actually running on each individual cluster. So if we lose one of the cluster members, we will have sub-second failover again, even from a layer 3 perspective. So from failover, although the 2 technologies are close, switch clustering is slightly better. If we look at complexity, switch clustering is slightly more complicated. And the reason is, again, if we look at the layer 3 protocols. In the case of a routing protocol like OSPF, we have 2 instances, one on each of the switches in the cluster. So there's an adjacency between them. It's just a little bit more things going off. If we look at stacking, it's one single switch. We don't have any adjacencies. There's no need to exchange routes between the units. Also, when we run a gateway redundancy protocol, VRRP, we need this on switch clustering because there are 2 switches. If one fails, we need the gateway to move between the 2 members of the cluster. With stacking, because it's acting as a single switch, we don't need any gateway redundancy protocol. So from a complexity perspective, again, stacking wins out here. So now let's look at switch replacement. What if we have a failed switch in a stack or in a cluster? Well, if a switch in a cluster fails, obviously we've got to go and replace it. We'll have to take the new switch, we'll have to put it on the correct software, we'll have to load the configuration onto it, we'll have to put it back into the network. So it's quite a manual process. With Exos stacking, if we replace a switch, the configuration file will be automatically copied to that switch from the other stack members. With the ERS stacking, if we replace a switch, the other stack members will actually handle the software upgrade and the config of the new replaced switch, so the process is fully automated. So from a unit replacement perspective, there are advantages with stacking over clustering. The final one is resilience. If we look at which of these 2 technologies is the most resilient. It's a very close call here, but with stacking, we actually have one config file. although it's shared amongst multiple units. So if, for example, there was a possibility of config file corruption, or if somebody makes a mistake when they're actually configuring the switch, with a stack, that error could potentially cause the stack to go down. With clustering, because we have two individual nodes with two individual config files that are independent of each other, the chances of a config corruption or a human error taking both switches down is much less. So when we look at resilience, clustering is actually slightly better than stacking in this case, and that's the reason that we generally use clustering in core and distribution configurations for customers' networks. So the next technology to look at is the extended edge. With the extended edge solution, we're actually using port extenders to extend the access layer of the network. We have a central switch called the controller bridge. This switch has all the intelligence of the network. The port extenders simply forward any traffic coming from user devices to the controller bridge where the traffic is processed, any decisions are made, and then the traffic is either sent onwards or back down to another port extender. We can connect up to 48 port extenders to a controller bridge, which gives us a total of 2,300 ports. So this is a very scalable technology and ideal for many enterprises. One of the benefits of this solution is that all of the configuration is centralized on that controller bridge. The port extenders are relatively simple devices. They don't even require an IP address. They have no configuration on them, and the small firmware on them is actually handled completely by the controller bridge. So one of the advantages with this solution is that somebody without a technical network expertise can be sent out to deploy the port extenders while the network engineer concentrates on configuring the controller bridge, which is all in one central location. If there's a failure on a port extender at a later date, we do not need a technical person to visit site. The person just needs to remove the failed port extender, put in a new one, connect the cables and power it up. It's really that simple. He doesn't even need to have a console connection to that device. This solution is ideal for north-south traffic. Any traffic that comes in a port extender has to be sent up to the controller bridge for processing and switching. So even if that traffic's coming back down to the port next door on the same port extender, it will need to go up to the controller bridge and back again. This makes this solution much more suitable for north-south traffic. However, if you think about the access layer of an average enterprise network, this is exactly what type of traffic it has. We have devices talking to servers in the data center, and then the server replies back. We see east-west traffic in data centers, but in campus networks, we see north-south traffic. So this is a very nice solution for the campus edge. The switch used as the controller bridge is generally quite a high-end switch as well. So all of the features that that controller bridge switch can support on its ports can actually be used on the ports of the port extenders. So we can have a very rich feature set on the relatively inexpensive port extender ports because the controller bridge is doing the processing. Many of the features that we need in enterprise, such as 802.1x, quality of service, advanced ACLs, policy, fabric attach, can be used on the port extenders because it's the controller bridge ports that are actually doing the processing. The port extenders for this solution are actually the V400 series, and they're available in both 24-port, 48-port, PoE and non-PoE. The extended edge can also have some interesting topologies, as we see on this screen. So the basic topology, just here, has a single controller bridge and then some stacks of port extenders that are connected back to that single controller bridge using a link aggregation group. This is the basic configuration. However, if we put two controller bridges in and configure them in a multi-chassis lag or a cluster, we actually can connect our port extender stacks to different controller bridges. And this removes the single point of failure of a controller bridge. We now have a redundant solution. If we look at the topologies on the right of the screen, we can also support rings. We see in the first example a basic ring, and this can have many port extenders in. And then the second example is a redundant solution with dual controller bridges and multiple rings. This is a very flexible deployment method and can be suitable for customers that have unusual topologies in their campus. The next feature that we can use in the IP campus networks is EAPS. This is Extreme Automatic Protection Switching. It's actually a technology that allows us to build redundant ring topologies with switches, and these rings have sub-second failure. It provides a sort of similar function to spanning tree, apart from the recovery time is much faster. Each ring can carry many VLANs, so we can support multiple services across these rings. But do bear in mind these are layer 2 rings, so we would need to do the routing somewhere else. However, in certain topologies they can be very useful. We have a concept of a master bridge, where one of the switches is actually the master for the ring. He's monitoring the ring, and if there's a break in the ring, it will recover the traffic very quickly by opening up one of the blocked links. There's also a standards-based version of this protocol called ERPS, Ethernet Ring Protection Switching, and this can be useful if we need to interoperate with other vendors. At first glance, this technology can look very similar to the extended edge. However, it's quite different. EAPS rings are using fully functioning Ethernet switches from the Exos range. They can also be integrated with the ISW switches, the industrial switch ranges, which can be useful when a customer has ring topologies, for example, the boundary of a university where they need to deploy CCTV for monitoring. The port extender solution is proprietary. It can only be used with other extreme switches and extreme controlling bridges. So, whilst these two technologies might look similar at first, there are subtle differences that are important. With the EAPS, we also have a number of topologies that we can deploy. You can see some more complicated ones here. So for example, at the top, we have 2 controllers rather than a single controller, so we have controller redundancy for the ring. Also, a pair of controllers can support multiple rings. And actually using that, we can build quite complicated networks, as you can see at the bottom, with rings attached to rings and so on. So this is quite a flexible technology that can be deployed on difficult topologies in the network. So now let's look at the basic network designs, and there's really only 2 that I want to show you. Enterprise networks can be extremely complicated and varied, but generally speaking, there's 2 designs that we use most of the time for medium enterprise customers. The first one is the collapsed core. You can see the example here. We have a pair of core switches. The pair of core switches is either clustered or stacked, and they have a routing instance on them, doing the routing between the different VLANs on the customer's network. Here we have the stackable switches used in the IDFs, where the client devices are attached. And these stackable switches are connected back down to the core using a lag, a redundant active-active link that load balances the traffic. On this side, we have the server connection. Now the server could be connected directly to the core, depending on the port density required, but what's more normal is we'll actually add some top-of-rack switches, and the servers will connect to those. The top-of-rack switches are then redundantly connected by link aggregation back to the core of the network. You'll notice that all the routing here is done on the core between the 2 core switches, and since each core switch will have an IP interface into each VLAN, we don't require any routing protocols here. This is straightforward network and is used by many enterprise customers, for example, small business, hospitality, etc. The next type of design I want to look at is a 3-tier network, and this is typically used in the larger enterprise customers. Again, we have a campus core. We can see this pair of core switches here. Usually we would be using clustering technology here. 2 switches to provide redundancy and active-active traffic load sharing. In this case though, we have a distribution layer, as you can see here. And actually, in this case, we have 2 distribution pairs which would cover maybe 2 separate buildings. We could have many distribution pairs connected back to the campus core. Again, the access layer looks very similar. It's dual attached using lag to the clustered pairs of switches in the distribution layer. Again, for the servers, we have some top-of-rack switches which are redundantly connected back to the campus core. The main difference here is we need an active routing protocol. Unlike the collapsed core, we have multiple clusters of switches, and the VLANs that are defined on the different clusters of switches are not the same. So for example, if we look at the IP subnets that are available on the core switches, they will not be the same as the IP subnets that are available on distribution 1 switches or distribution 2. So typically we would configure a routing protocol such as OSPF across the links here so that these cores can form routing adjacencies and exchange routing information. We may also optionally configure the PIN protocol if we require multicast routing on this network. If we look at the areas of this network, one of the reasons that we would deploy this design of network is we've got different buildings. If you see this zone here, this could be one building, the next zone could be in a different area of the campus, and then the final zone where the core switches are could be a data center. So we use this three-tier design when the network is geographically dispersed. The final point that I want to make is that we can mix and match these technologies. If you look at this example here, we're using switch clustering in the core and the distribution. We're using stacking in the top of rack for the server farms. And then if you look into the access layer of the network, we're actually using EAPS rings at the top of the diagram. These could be, for example, the boundary of a building where we need CCTV monitoring. And then towards the bottom, we're using the port extender technology, extended edge. This is allowing us to collapse all the configuration into the distribution pair on the lower part of the slide, as I'm indicating here. So when we're using these technologies, they're by no means mutually exclusive. We just pick from the 4 different technologies that are available to build the best type of network that suits the customer. That concludes this session for Extreme IP Campus. Thank you for watching.